occurred. Oh. All right. Can you hear me clearly? Forgot to put on my headphones earlier. Yeah, good. All right, cool. And I hope, yeah, I think it's recording. So that should be okay. Right. Okay, so I hope you had the chance to go over the questions. And now let's look at the solutions. Here, the first question is a pole vaulter. He's holding a pole as shown in the figure here. The free body diagrams are given. So as I've mentioned earlier, the free body diagram here on the right, this one is appropriate. Let me just admit. Okay, so as I've mentioned earlier, the free body diagram here on the right, where you're just representing the pole as a dot, is more appropriate for if you're using net force. More for F net is equal to 0. And when you need to consider torques, then you have to use the extended, I want to call it extended free body diagram, where the exact positions of the forces are indicated along the object. So you have the weight force, of course, because of the mass of the pole. You have a downward weight force, and it's at the center of gravity, roughly at the middle of the pole. Then you have the left hand that's exerting an upward force, and the right hand that's exerting a downward force. The first question asks us to explain why the right hand exerts a downward force on the pole. Why isn't it? Yeah, if you notice, the hands are also sort of oriented opposite each other, so that the forces that the hands are exerting on the pole are opposite, directly opposite each other. So why do you think so? Okay. It has something to do with stability, right? Hopefully you've seen, I don't know if you noticed, but if about the pivot point, you have two forces that are opposite in direction, those opposite forces will provide counter torques, right? So one torque, for example, if you take the pivot point to be the weight, or at the end of the pole, for example, the force on the left-hand side will provide clockwise torque, whereas the force on the left will provide an anti-clockwise torque, right? So you have counter torques that can satisfy net torque is equal to 0, and you will have equilibrium. So that's the reason why. Now let's go to the next question. So the pole has a mass of 5 kilograms, and its center of mass is 1.2 meters from the pole vaulter's left hand. Okay, I have a bigger drawing here. Find FL, which is the force exerted by the left hand, and the distance between the hands are given to be 0.90 meters apart. Okay, so first step, free body diagram. We're given here a free body diagram, but just check whether all the forces have been indicated there. So you have weight force because of the mass of the pole, and that's a downward weight force. And then you have this FL force from the left hand and FR force from the right hand. And I think there's no other force that we need to draw to complete the free body diagram. It's already complete there. Okay, once you have the free body diagram, how would you answer A? So you can say that the force, the downward force from the right hand provides a counteracting torque to the upward force from the left hand. to the upward force from the left hand. And you can expound further if you can say so that the net torque will be 0, but that should be sufficient for a short answer. Right, good. Yeah, okay. So here we have the free body diagram. We are given the mass. Okay, so we'll try now to simplify our free body diagram if we can. We're given the mass, so we can find the weight force is equal to mass times gravitational acceleration. Right, 5 kilograms times 9.8 meters per second squared should give you 49 newtons for the weight force. You have here weight force is equal to 49 newtons. Okay, right, so next is to choose your pivot point. Okay. Here we go with choosing the pivot point. Okay. We want to find FL. Where do you think should we put the pivot point? A sensible choice would be to put the pivot point at FR because, yeah, we know weight. We can solve that from the mass. We don't know FR and FL. And so to eliminate one of these unknown forces, we put the pivot point there. We cannot put the pivot point in FL. Well, technically speaking, we can put the pivot point at FL that will allow us to find FR, but then we need to do an extra step to find FL, right? So since we are explicitly asked to find FL, then we might as well put the pivot point at FR. That eliminates one of the unknown forces that eliminates FR, and that will allow us to solve for FL. Yeah, so FL, we should then balance out the torques about the pivot point. So clockwise torque should be equal to the anti-clockwise torque. Right, so FL, looking at FL is upwards. It will tend to rotate the pole in an anti-clockwise direction about the chosen pivot point. Right, whereas the weight force will tend to rotate the pole in a clockwise direction about the chosen pivot point, which is where the right hand is. Okay, right, so clockwise torque, that means we need to find the moment arm. Clockwise torque is provided by this weight force. Okay, that means we need to find the moment arm of the weight force. Sorry. Right, so that means we need to find the moment arm of the weight force, multiply that with the force itself. Okay. And for the anti-clockwise torque is provided by this upward FL force. That means we need to find the moment arm of the FL multiplied with the FL force itself. Okay. Right, so RW, okay, this is our force, weight force, and our chosen pivot point is here. So you can just, you can relocate your pivot point wherever it's convenient for you, as long as it's along that same vertical line, so that wherever it's convenient for you to draw a line or a distance that's perpendicular to your weight force and passing through your pivot point. So this will be RW. If you want, you can also draw your RW here, okay, from your weight force to the pivot point. That will be RW. Okay. But if it's difficult to visualize that, you can always relocate your pivot point along a straight vertical, along the vertical axis. The key idea is that the moment arm and the force should form this 90-degree angle. Okay, now how do we find RW? We're given that the pole vaulter's hands are 0.90 meters apart. And I think the length of the pole. Yeah, here. The pole has its center of mass at 1.20 meters. Okay, so that means that the center of mass from the pole vaulter's left hand is 1.2 meters. So that means from here, from the center of mass to the left hand is it's 1.2 meters, and then the distance between the hands is 0.9 meters. I hope that's visible right there. Okay, so therefore RW, okay, RW is from the pivot point from the right hand to the center of mass, right? So we have to add these two. So RW will then be equal to 0.9 meters plus 1.2 meters. So RW 0.9 plus 1.2. Okay, right? So lever arm, it's from the pivot point, which is at the right hand position of the right hand, to the force. In this case, it's the weight force. So it's this whole length here. That's why we had to add the distance between the hands and the distance from the left hand to the center of mass. Okay. And we multiply RW, the lever arm, with the weight force, which we solve to be 49 newtons. Okay. Right, that's equal to the anti-clockwise torque. We're now looking at the anti-clockwise torque is provided by FL. So we need to find the lever arm for FL distance between pivot point and FL, which is given to be 0.9 meters times the force itself, FL, which is what we want to find. Yep. We know everything in the equation except FL, so we divide both sides by 0.90, and that allows us to cancel 0.90 on the side, and we will be able to find FL will be about 114 newtons. Okay, any question about the solution for this? If you have any question, you don't have to wait for me to finish. You can just type it in the chat box and then we can address it as we go along. Okay, if in case you were asked to find FR, then you can either put the pivot point at FL or you can use net force is equal to 0, in which case the upward force FL should be equal to the sum of the downward forces FR plus weight force. And you can rearrange this to isolate FR by subtracting FR on both sides of the equation. Okay. To eliminate FR, because FR minus FR will give you nothing. And then oh no, that's sorry, it's actually FR we wanted to find. So we should subtract both sides with the weight force. Okay. To isolate FR, so weight minus weight will give you nothing. And then you have just FR is equal to FL minus the weight force. That's if you were asked to find FR. And that's how you extend the solution for that. Okay, I don't see any question in the chat box, so let's go to the horse question. Okay, this horse question is always driving students crazy. So So let's go through it. Okay, right. We're given the mass of the horse. It's 400 kilograms and it's leaning against a wall. And we want to calculate the force exerted by the wall. So it's this F wall that's illustrated in the free body diagram. And it's pointing to the right. Okay, we're given the weight acts at the center of mass or center of gravity. That's what CG means. It's directly downwards. Of course, we can solve for the weight force because we're given the mass. Okay, the first step is to draw the free body diagram. It's given already here, but just check whether there are other forces that are not drawn in the free body diagram. Do you think there are other forces that we should indicate or include in the free body diagram, but it's not given in the problem? Do you think there are? First of all, what is the object here? Okay, so we want to calculate the force the wall exerts against the horse, right? So we're looking at the horse, we're looking at the stability of the horse. So the horse is the object here. So we need to consider all the forces that are acting on the horse. We are given the weight force and the support force from the wall, but are there other forces that the horse experiences? Yeah, very good. Yeah, very good. You have the support force from the ground. So notice how the horse is standing on the ground. So there should also be a normal force. And normal force is always directed upwards, perpendicular to the ground or the support, which is the ground. Okay, the force the horse exerts on the wall, that's a consequence of Newton's third law of motion, right? So the wall exerts a force on the horse that's to the right. As a consequence, the horse exerts a force on the wall that is to the left. Okay, so you're right, there is a force exerted by the horse on the wall and it's to the left, but the force is exerted on the wall. Okay, it's not exerted on the horse. In your free body diagram, we just draw the forces on the object. Our object is the horse, so it should just be the forces on the horse. So that means we should not include the force on the wall that the horse is exerting, although it is there, right? Okay, there is one other force. It's the force that prevents the horse from slipping. It's the force that prevents the horse from, falling, slipping. Yeah, forgive my accent. What I mean is this one, so that the horse will not slip. There should be a force that prevents that slipping. Okay, if the horse were to slip and fall down, the tendency would be for the horse to slip to the right. Okay, if it were to slip, so there would be a tendency for motion to the right. Okay, but that doesn't happen because there is a frictional force that is counteracting that possible motion to the right. Okay, so there should be a frictional force to the right that's exerted on the hoof of the horse. Okay, so let me just tidy up. Okay, our free body diagram here. Okay, right, so those are two additional forces that you should incorporate that's not given in the figure here. Now, when we draw the free body diagram for finding torques, as you noticed in the problem with the extended arm in the lecture that we did, what I did was to redraw the free body diagram so that it's neater. So let me just redraw the free body diagram here. Instead of drawing the horse, I represent the horse with this diagonal line that you see here, this blue diagonal line. And I indicate all the forces acting on the horse. So this is like the horse. Yeah. is indicated by this blue diagonal line. So there's a center of mass, the weight force that's acting about the center of mass. Okay, so I'll draw my weight force that's directly downwards. Yep. And then I have the support force from the wall that's directed to the right. But notice how the force from the wall is lower than where the center of mass is located, from where the weight force is acting. Okay. And remember, when you're drawing free body diagrams for torques, you have to put the forces at the positions where the forces are acting. So you should have F wall to the right that is lower in position compared to the weight force. Okay, and then at the hoof down below, you should have your normal force that's upwards, and you should have your frictional force that's leftwards. So that's your free body diagram. So it now looks neater compared to the one with the horse. If you want, you can also indicate these distances. So why don't we put that in our free body diagram? Okay, so the weight force is 0.35 meters away from where you have your normal force and the frictional force. So this will be 0.35 meters. Okay. The force from the wall to the ground, this one to the ground, this is 1.2 meters. And the center of gravity or center of mass where the weight is acting is 1.4 meters from the ground. Okay, so that's your free body diagram with the distances indicated if you want to draw that. Okay, so next step after having the free body diagram is to pick a pivot point. So what do you think is a sensible pivot point to choose? Where would you put the pivot point? The weight force, you can solve the weight force, right? Because you're given the mass of the horse. So you can, in principle, solve for the weight force. The force on the wall, that's what you're asked to solve. Okay. And so it will be sensible to choose the pivot point at the position of the normal and the frictional forces, because then by putting the pivot point where the normal and frictional forces are, we eliminate right away two forces that we do not know. Okay, right, so we choose that pivot point right there, and then we do the balancing of torques. Okay, so clockwise torque should be equal to the anti-clockwise torque about the pivot point. All right, so if you look at the weight force is pulling the horse downward. So if it were to make the horse rotate, the weight force will sort of cause the horse to rotate in an anti-clockwise manner about the pivot point, right? Whereas the wall is pulling the horse to the right. So if the wall were to make the horse rotate, if the force on the wall were to make the horse rotate, then it will make it rotate in the clockwise direction about your chosen pivot point. Okay. All right. Does that make sense so far? Yep. Okay, so clockwise torque should be balanced by the anti-clockwise torque. Clockwise torque is provided by the force on the wall. So that should be the moment arm between the force on the wall to the pivot point times the force on the wall itself. Okay. And that should be equal to the anti-clockwise torque. It's provided by the weight force of the horse. So you should have the moment arm between the weight force and the pivot point times the weight force itself for the anti-clockwise torque. Right, now finding the moment arms. What's the moment arm for the wall? Okay, so the wall, the force on the wall is this one. It's to the right. Okay, and your pivot point is down here. So you draw your moment arm perpendicular to your force and passing through your pivot point. So let me see if I can get a different color pen. So if you go from the force going down to the pivot point, this should be the moment arm for the force on the wall. Okay. And you can see that's exactly 1.2 meters, right? The distance from where the wall exerts a force to the ground. So the moment arm of F wall should be 1.2 meters times the force of the wall itself. Right? Okay, and then for the anti-clockwise torque, it's the weight force. Okay, the weight force is exerted 1.4 meters above the ground, but the weight force is also 0.35 meters away from the hoof, from where the normal and the frictional forces are. In essence, it's 0.35 meters away from where we put the pivot point. Okay, so weight force is down here. Yeah, if you extend the weight force further down like that, then you can see that the perpendicular distance between the weight force and your chosen pivot point is actually this distance, right? So this will be the moment arm of your weight force, and you can see it's 0.35 meters. It's the distance between the center of mass where weight force is acting and your chosen pivot point, right? So moment arm for the weight force will be 0.35 meters times the weight force. The weight force you can calculate from the mass, 400 kilograms times 9.8 meters per second squared. 400 times 9.8 gives you 3920 newtons for the weight force. Okay. Right? So therefore, we can now solve for the force from the wall by dividing both sides by 1.2. F wall times 0.35 divided by 1.2 is 1143 newtons. Yeah. Okay, so this is an example of how a smart choice for where you put the pivot point can simplify the problem, because then you can eliminate unknown forces that you don't have to worry about. Okay, so yeah, I hope that makes sense. Right. Are we happy with that solution? And can we move on to the next question? No questions. I also don't see any thumbs up, so I don't know whether that's a bad sign or a good sign. Yep, okay, right. I guess the trickiest part here would probably be finding the liver arms. But yeah, let's move on to the next question. Okay, we have here a man doing push-ups. The mass is given. The mass of the man is given 70 kilograms. Free body diagram is partially given, where you have the weight force acting at the center of mass. That's 95 centimeters away from the feet, and 42 centimeters away from the arm, from the hands. And it says here, determine the support or normal forces that the floor exerts on each hand and foot, and ignore frictional forces. Okay, so that means that our free body diagram is not complete. Okay, the problem indicates that there should be a normal force upwards on the hands, supporting the hands, and there should also be a normal force that's supporting the feet. Okay, so let me just redraw the free body diagram so that it's less cluttered, where you have the weight force that's downwards, and then you have the normal force on one end. Normal force on the hands, and you have the normal force on the feet. Okay, I'll show the given distances from the hand to the center of mass, or the weight force. That's 0.42 meters. I'll convert that to meters already. And from the center of mass to the feet, that's 0.95 meters, or 95 centimeters. Okay, from what's given, you can find the distance between the hands and the feet, 0.42 plus 0.95. That will be 1.37 meters for the distance between the hands and the feet. So you have this free body diagram here, and we're wanting to find both NH and NF. Okay, so we don't know these two. That's what we want to find. So we're given the mass. So as usual, we can find the weight, mass times gravitational acceleration. The weight is given to be 70 kilograms. 70 kilograms times 9.8. So we have a weight force of, 70 times 9.8, 686 newtons for the weight force. So we can already put that, 686 newtons for the weight force. Okay, so first let's find the force on the hands. Okay, find the force NH. Okay, so in that case, we put the pivot point at the other unknown force. That will allow us to eliminate NF and allow us to find NH. Okay, so NH, about the pivot point at the foot, NH will tend to rotate the man. Okay. Just extend that about the pivot point NH will tend to rotate the man in the clockwise direction, whereas the weight force will tend to rotate the man in an anti-clockwise direction about the pivot point. So clockwise torque should be equal to the anti-clockwise torque. Clockwise torque is provided by NH. So that will be the moment arm of NH times the force NH itself. That should be equal to the anti-clockwise torque. It's provided by the weight force. So it should be the moment arm of the weight force times the weight force itself. Right? Okay, moment arms for NH. Okay, your pivot point is at the position of NF. So moment arm and NH is vertical. So the moment arm goes from your NH. Let me change colors. Okay, from your NH, it should go towards your pivot point. You can always relocate your pivot point along the vertical axis, just so you can draw this moment arm for NH. Okay. Notice how you have a 90-degree angle between your moment arm NH for NH and the NH force. Okay. And that's the distance between NH and NF, which we solve to be 1.37 meters. So that's 1.37 meters for the moment arm times the force NH that we don't know. All right, and then for the anti-clockwise torque that's provided by the weight force, you need to sort out the moment arm between the weight force and NF. Okay, so if you draw a line from your weight force to NF, you can always relocate your pivot point along a vertical line. Okay, notice you have this perpendicular angle between weight force and the moment arm for the weight force. Okay, and you can see that should be 0.95 meters times the weight force itself, which we calculated earlier to be 686 newtons. So we can now solve for NH. It's the only thing we don't know. Divide both sides by 1.37, 1.37 on both sides. Okay, eliminates 1.37 on the left. Then you should have NH is equal to 475.69 newtons. Okay. This is for both hands. Okay. Because this NH force supports both hands. For a single hand, for one hand, simply divide that NH by 2. So for NH, for one hand, NH of one hand is equal to 475.69 divided by 2 is 343. 238 newtons. Okay, right. And then for the feet, okay, we already have 238 newtons. I'm sorry, we have 475.69 newtons for both hands. So here NH is 475.69 newtons. Okay, and NF is the only force we don't know. So you can use net force is equal to 0. So the upward forces NH plus NF should equal the downward force weight force. So that means we can use net force is equal to 0 or upward total upward force should be equal to downward force. We have force of the hands plus force of the feet should be equal to the weight force. Let me just put more space. Yeah, if we rearrange this equation to isolate, that's NF. Okay, we rearrange this equation to isolate NF because that's what we want to find. We subtract N hands on the left side. We also have to subtract N hands on the right side. So N hands minus N hands is nothing. So we only have N foot on the left is equal to weight minus the force from the hands. Okay, the weight force, we calculated that to be 686 newtons, 686. Let me just put more space here. 686 newtons minus N hands, we solved that earlier for both hands to be 475.69. Okay, so that gives us N feet is equal to 210 newtons, but this is again for both feet. So for 1 foot, we have 210 divided by 2 will give you 105 newtons for 1 foot. Okay. Right. So yeah, question 2. Right. Any question about what we've been talking about for the solutions? Because I guess we've run out of time to look at question number 4. The solutions will be up on stream, but I can also put up a video walking you through the solution to question 4. Because for question 4, this is the complete free body diagram. It's given to you, but all the forces are acting at a single point. If you notice here, if you extend the force FV via this dashed line, it intersects both the weight force and FM at this center of mass at a single point. Okay, so you only have one point of intersection. That means you cannot choose a pivot point, right? So you cannot put the pivot point at the center of mass because then that eliminates all the forces. And then that leaves you with nothing. So the strategy for solving this is to use net force is equal to 0. But you have diagonal forces. So that means you have to find the X component for the forces as well as their Y components, Fmx and Fmy, and do that as well for Fv. You should also find its X component, Fvx, and also its Y component, Fvy. Okay. And then do net force along the X, Fmx minus Fvx is equal to 0. And right along the vertical, you have Fvy. It's the one that's pointing upwards, minus Fmy, because Fmy is pointing downwards, minus the weight force. Weight force is pointing downwards, should be equal to 0. Okay, so this is how you solve this problem. But okay, right, I'll get to that question, but we don't have time. So I will put up the recording for the complete solutions to the last question on screen. How do you decide how many significant figures to include when recording your answer? You decide by looking at the least number, the smallest number of significant figure that's given. So for example, in question 1, this question 1. Okay, we're given 5.0. This is 2 significant figures, right? 2 significant figures. 1.20 meters. This is 3 significant figures. So that means when you round your final answer, it should have 2 significant figures because the least number of significant figures in the given is 2 significant figures. So roughly speaking, your FL, if you have to round that to correct number of significant figures, 110 newtons for FL. Okay, yeah. Does that answer your question, Hein? Yep, right. I'm not so conscious in rounding up the answers here. Maybe I should be. Yeah, but that's how you round the significant figures. I was more concerned on the process of solving the problems. Yeah. Cool. Any other question before we end the session? And then, yeah. Right. Yep. I don't see any other questions in the chat box. So we can end this session. If you want to join the revision session where we look at some revision questions for the test that starts at 1 o'clock, access the same Zoom link. Otherwise, where will we put the pivot? For the last question, so Amun, for the last question, you don't put the pivot somewhere else. Okay, because there's only one place to put the pivot, it's at the center of mass, but you cannot, if you put the pivot point at the center of mass, that eliminates all the forces, because all the forces intersects or pass through that center of mass, which is the only point where you can put the pivot point. So you cannot solve question 4 by using torques. The only way to solve question 4 is to use net force is equal to 0. Okay, but for you to do net force is equal to 0, you have to break down the diagonal forces into horizontal and vertical components, and that's where you have to put upward. The FMX is rightward force. Rightward force should be equal to leftward force, and downward forces should be equal to upward forces. Okay. So the way to solve question 4 is net force is equal to 0. You cannot solve it using torques. Yep. Okay, cool. Right. Okay. No other last minute questions. So we'll end the session. I'll see you. Have a good weekend if I don't see you in the revision workshop. Otherwise, I'll see you in less than an hour. All right.